In this video we will look at parametric mapping, an extension of kinetic modeling. And the example we will go through will be making maps of serotonin transporter density using reference tissue based modeling. Parametric mapping is the application of kinetic modeling in every image voxel of a dynamic PET series. This creates new 3D images in which the voxel values directly represent a quantitative parameter from the model. For example, instead of kilobecquerel per cc or SUV per voxel in an FDG PET, the result of parametric mapping could be an image with quantified glucose metabolism, in other words with the units micromole glucose per mil of tissue per minute per voxel. In this interesting example provided by Bob Cooper at the PET pharmacokinetics course, you can see how parametric mapping also separates components involved in the tracer kinetics. For this tracer DTPZ, when you look at the average images in the top of the image on the right hand side, you see that there is a mixture of signal if you only look at average images for a certain time point. If you apply parametric mapping, then you can separate out the BBB transport, represented by K1, and the VMAT2 binding, represented by the binding potential. Beyond interesting image presentation, parametric mapping allows image-wise averaging and subtraction within groups or for longitudinal measurements for single subjects. This allows clear visualization of treatment or pathology effects and can support statistical parametric mapping, in other words voxel-wise statistics in the same style as functional MRI. In this exercise we'll calculate parametric maps of BPND and we'll use the Logan reference method. All of this takes place in the PXMod tool. The PXMod tool is organized with tabs, seen here starting in the upper left, and on the name of each tab we can select the model that will be used. Within the tab we have sub-tabs taking us through the modeling workflow, and as you've seen in other tools, in the lower right we have workflow buttons that will guide us through that process. For this example we first set the model that we will use, and this will be calculation of the binding potential non-displaceable using the Logan reference method, and the method is selected using the menu drop-down right next to the name. Additional information about the model and its implementation can be found in our online documentation, which can be called up using the question mark next to the model name or found via doc.pmod.com. First, we define the image data using the Input Data Settings button in the Image Data tab of the workspace. In the dialog window, we should make sure that Input 1 in the top left is set to Database, and then we can use the file browser using the button at the end of that line to search the database for our example data. We'll use the demo database, and the subject we use will be pkin2, so you can use the subject name filter within the database, and for the subject pkin2 we will select the dynamic DASB PET. When you set the series, it appears in the previous dialog. We don't need to apply any pre-processing, so we can reset the loading parameters, and then when we press OK, the image will be loaded. The load button indicated just below the loading settings is actually part of running a protocol, so we don't need to press load again. We see the dynamic PET displayed on the Image Data tab, and the next step is to calculate a mask, which will be used to limit the calculations to the brain voxels. So we can proceed using the masking workflow button in the lower right. And on this masking page, we will define a mask of the brain so that we only include the voxels from the brain. Creating an average image that resembles the whole brain can aid threshold-based masking, and such an average can be created from a time range where the tracer concentration is high throughout the entire brain. This is often the first minutes after tracer injection when the concentration in the blood pool is high. For tracers with a low extraction fraction, it may also be a middle time range, while for trapped tracers like FDG, it could be a late average. For this example, we can average the frames 10 to 20 by entering those values in the averaging tool just in the lower right of the Input tab, and then we click Average to create that average image. We then get moved to the average tab, seeing the result of our average of frames 10 to 20, which gives us a reasonable outline of the uptake throughout the brain. To create the mask, we'll use the thresholding method, seen in the lower left. We can use a simple threshold of greater than or equal to and enter 10 kilobecquerel per cc before calculating the mask with the segmentation button. On the mask tab in the top right, we see that there are some small holes in this mask, although the overall outline is good, and we can close those holes using the morphological closing method, which has a range of pixel sizes. In this case, 3 pixels is enough to close some holes without expanding the contour of the brain, and then we rerun segmentation with the morphological closing. The mask that's created should be saved to the database so that it can be used in protocols later. That's why we have a warning about not saved on the right hand side. So I'll change save mask to database, and I'll save the mask to the demo database. I can use edit info to indicate that this is from my test workflow. And then save. So we get confirmation of saving, we see the warning disappear. And now we can proceed using the time activity curves, the tax workflow button. In parametric mapping, the time activity curves, and particularly the reference tissue time activity curve, are used for the model preprocessing and eventual application in all voxels. In the VOIs list, on the VOI tax tab, we see a list of 3 empty VOI definitions, and these originate from the model we're using. We have TAC1 for a receptor-rich region, a reference tissue VOI, and then as an alternative to a target tissue, we can use a VOI in which K2' will be determined. This is the reference tissue washout rate. VOIs can be drawn or loaded, and it's important that we pay attention to the reference tissue VOI, since the reference tissue curve will be used for modeling in all voxels. As indicated, a target tissue VOI is not always necessary. We can use this VOI in which K2' will be determined, or we can also enter a K2' that we've previously defined from kinetic modeling. Select Load VOIs and locate the DASB regions VOIs in the demo database for this subject. This contains many regions, and we can perform some processing to make them useful for the next step. The cerebellum will be our reference region, and we can average all of the remaining VOIs into a region that we will use to determine K2'. To do this, we can move to the Group VOI tab, and we can use Shift and click to select all of the VOIs except the cerebellum, and then create a union VOI. We now have a reference region VOI and the VOI in which we will determine K2'. So now we're ready to proceed using the Prepare Tax Workflow button in the lower right. Here we see a preview of our time activity curves, but we need to make sure that the correct selections are made in the top part. Target tissue can be deactivated. For reference tissue, we should have cerebellum selected, and the VOI in which K2' is determined should be our union VOI. We have to save either a VOI or a time activity curve before proceeding so that they're identified for the protocol. Generally, we recommend saving the VOIs, and we can do this using the Save shortcut in the top center of the tool. Save the cerebellum VOI to the database as DASB cerebellum. You can indicate that it's your test run instead of adding confusing entries. And similarly for the union VOI, which we can identify as our DASB K2' region for our test workflow. Note that nothing is ever overwritten, even if we use the same name. Now the warnings on the right hand side about not saving the voids have gone, so we're ready to proceed to the modeling step. Again, we have a workflow button in the lower right. On this Model Preprocessing tab, you can note that the VOI for reference tissue and VOI for K2' have been set according to what was just saved. If you for some reason don't save the previous VOIs, you should use the load dialog to identify which VOIs you will work with. Below the VOI selection, we see the parameters for modeling. The T-star parameter represents the start time of the data segment used for the estimation of BPND in the Logan reference model. And if we don't use a target tissue, this should be a fixed value. The K2', the washout rate constant of the reference tissue, will be calculated as the median K2' of the VOI pixels in a BP, so binding potential range. And SRTM mapping will be performed in the union VOI to give us those K2' values for the median calculation. All of these parameters can be set to the recommended default values with the button in the lower left, and then we can adjust them as necessary. So the selection to calculate K2' is correct, then K2' will be adapted from this starting value, and we can deactivate T-star and set it to 10 minutes based on previous exploration of the data in the kinetic modeling tool. Now we can start the pre-processing with the Preprocess Model workflow button. This will take a little bit of time while it calculates the SRTM maps. Once the maps have been calculated, we're taken to the Model Results tab, where we can see a preview of our reference tissue curve and confirmation of the fixed T-star that was used. On the SRTM Maps tab, we can see the maps that were used, particularly the BPND map from the SRTM model that was used to calculate our K2' median. And now we can continue to set the map configuration using the workflow button. The checkbox indicates which maps will be calculated. In this case, for this model, we only have 2 available, but this list could be much longer depending on the model selected. We want to calculate the BPND map, and we can use a reasonable range. In fact, 60 is already a very high upper threshold. And then we can start the calculation using Start Pixel-Wise Calculation in the lower right. The resulting maps are then shown on the Parametric Maps tab, and the Data Inspector can be used to quickly inspect the BPND values. The maps can be saved in one of the available formats. We typically recommend saving them back to the database for good study organization. We have a save icon on the right lateral taskbar, or you can use the save settings in the center right of the tool. During the saving process, PMod will add information about the model parameter to the series description or to the specified file name, depending on the output format. In this case, we see that the series will be identified as the BPND map for this dynamic DAS PET series. We highly recommend saving the full processing configuration so that you can retrieve all of the processing details later, edit them if necessary, and then repeat the processing. This is done by saving a protocol using the button in the center of the tool in the status line. In the dialog that opens, we use the database to save our definition. This will be BPND for the Logan reference model, and this is also our test run. To test that protocol, we can open a new workspace, also illustrating that we can have multiple workspaces in parallel in Pixmod. At first it copies the same model, and then we can use the Load Protocol button at the bottom of the tool, select our most recently saved protocol, the BPND Logan Ref test, and then this will confirm which data is used. Here you see why we saved the mask and whether we execute immediately or not. I'll execute the protocol, and the tool will run through the processing until the map stage. Now we see the same BPND map that was calculated, and of course we could save these maps and verify in the other tools that they're exactly identical.